So hello and welcome to exam review. Yeah, we have an exam this Friday. And so my plan right now is to go through last year's exam and do the whole same thing. Those you had me in physics 1 before, same idea. I'm going to give kind of some hints on grading. I don't have my exact grading rubric here because it's in my office at Delhi and I haven't been to Delhi or my office in what seems like an infinite amount of time. But I can give a general idea of what I gave partial credit for by memory, best I got. This version I'm going to be doing is, a PDF of the exam. Keep in mind the exam for you is not quite going to look like that. The exam, when you go to take it, which is going to, on Friday, the October 2nd, it's going to upload right at 3 o'clock. And you can find the exam right here. I mean, I could hit this now, but it won't let me do it yet. But it'll be right here at 3 o'clock, and it'll close at 4:05. Solutions will be posted that evening. I hope to grade it. I'll grade it sometime that weekend. I won't guarantee when that weekend, but it'll be graded before Monday. To show you what the exam is going to look like online, the exam I'm doing right now, the fall 2019 one, I put it up in this format. Basic setup is when you go in, the first page is just kind of some information. And then after that, each page in here is one problem. What I'm going to ask is you do it on paper, just like I'm about to do here. And then you take a picture of your work and upload it. And just upload one picture per problem. There'll be 4 problems, one from each of the 4 chapters. More hints than that I'll give as I go through them. Any questions on the format before I get started?
Nope.
Okay.
Nope.
So the first problem will be something from chapter 20, which means it's going to either be Coulomb's law or electric fields or some combination of the both. And this is the one I did last year. Now, once again, they're not going to be exactly the same. I'm giving you the exam. I'm going to change up my problems, but it's going to be some combination of those, which means you're going to have to do with vectors. So let's look what I did last time. I said 3-point charges are located on a circular arc as shown below. What is the total electric field at P, the center of the arc? Include direction. Okay, if I want to find the electric field is KEQ over R squared. But I recommend always absolute valuing your Q's, because there's no easy way to say what the direction is from this equation. The direction is going to come from looking at this picture. See, what we know is that electric field always points away from positive charges and towards negative charge. So at point P, Q1 is going to cause an electric field pushing away from that. Pushing away because it's positive. At point P, Q2 is going to put an electric field towards it. It's going to be towards it because Q2 is negative. And at point P, Q3 is going to put another electric field pushing up and away. And now it's also away because, once again, positive. Now, I didn't actually put any labels on that, so here you go. Here it is with labels. And I can say these are the electric fields. 1 is away from 1, 3 is away from 3, but 2 is towards 2. But these are vectors. I'm looking at these vectors, and I'm not even going to start solving this yet. I'm going to go back to physics 1 stuff right now and say, okay, I got some vectors I want to add. And usually I do, the whole right minus left, up minus down stuff, what is going on. And I see this E1 and E3, they're at some angle. I mean, I know the angle. They're both at 30 degrees respectively, because that's marked right on here, but they're not straight along X or straight along Y. So I'm going to take E1 and E3, and I'm going to say, let's not treat them like that. Let's break them into components. And say E3 is an E3X and E3Y. E1 is E1X and E2Y, where the E1X equals E1 cosine theta 1, and E1Y equals E1 sine theta 1, and the same thing for E3. I'm not going to bother doing that with E2, because E2 is just a long negative Y. So I don't need to worry about it. And I'll say this electric field, I'm going to turn to two electric field equations, one in X, one in Y. And I'll say in X, I'll have E1x plus E3x minus E2. In Y, it'll be up minus down. So EY will be E3y minus E1y. But let's look at this guy right here. If I look at this, E is going to be KEQ over R squared, right? Well, that means this is going to be KEQ sine theta over R squared and KEQ sine theta over R squared. But both 1 and 3 have the same charge. And they're both the same distance from P. And they're both at the same angle. And so what I'm going to say is that this is actually going to balance out. The y is going to cancel because they're the exact same magnitudes in opposite directions. And so I can ignore my y. It all cancels. And for x, I'll just stick to what I have left. I'll say it is KEQ1 over R squared cosine of 30 plus KEQ3 over R squared cosine of 30 minus KEQ2 over R squared, with no cosine on that one because that was the flat one. Of note, Q1 and Q3 are the same, and I kept the same R for everything because it's the same R for everything. So I could simplify this to be 2 KE Q1 over Q over R squared cosine 30 minus KE Q2 over R squared. If I wanted to simplify this, I could and say it's KE over R squared 2Q1 cosine 30 minus Q2. You don't need to do that step, but I like to simplify things. And I can plug in. What's all? Come on, where's it written? 4 centimeters. 3 nanocoulombs. Q2. Now I'm going to point something out here. Note that I plugged in a positive 2 for Q2. That's because, once again, I'm doing absolute value here. I'm not drawing my absolute value on every step, mostly because if I did, it just gets really messy and ugly. But theoretically, because I was doing that with the absolute value, there should be a whole bunch of lines there. The negative sign is just direction. I've already accounted for the direction, so I'm not going to bother putting it in again. And of course, my email just popped up over what I'm trying to do, so I couldn't read it. But anyways, I can plug in and get that answer. Now, of note, I got a positive answer. And I was assuming positives to the right. So it's to the right. Any questions? Okay.
Nope.
Now, as I said, this first problem is going to probably involve Coulomb's law, electric field, or both. Chances of both are actually pretty high. This one I started with electric field. Part B is that whole both part. And part B says, okay, what's the force on a charge negative 1.56 nanocoulombs? The force on something electric field is QE. And so it'll just be my charge, negative 1.56 times 10 to the negative 9 coulombs, times my electric field, 1.8 times 10 to the 4th newtons per coulomb, which gives me negative 2.8 times 10 to the negative 5th newtons or 2.8 times 10 to negative 5th newtons to the left. Okay, quick thing about grading for those of you who haven't had me before. I grade heavily on partial credit. This number, well, each problem's 25 points, right? If I remember correctly, this number was 3 points. This number was also 3 points. And the directions were each 2. That's only 10 out of 25. Most of my credit is for the work, and you have to show all work. If you skip steps, you won't get full credit because I give credit for the work. I don't remember, as I said, my solution manual with points marked down. I mean, I have my solution. This is on Banco Hall also, so you can see it typed. But my point breakdown is in my office at Delhi, and I'm not going back there because I'm not. But everything else would be all the partial credit would be all the work. Show your steps. I want to say it was like 5. It's like 5 here. Doing cosine and sine was like probably 2 and 2. Realizing y was 0 was some number of points. I forget the exact breakdown. Other thing, for those who haven't had them before, I grade each part mildly separately. There's no possible way to get B correct unless you got A correct for this problem. If you get A wrong and you use the answer you got to do B, you can still get full credit for B. I won't compound errors. So if you make a math mistake in A, you can still get full points for part B as long as you keep using the number you got. And yeah, that's the setup. As I said, I grade heavily with partial credit. Normally final answer, the final answer would never be worth more than 5 out of 25. That's the most. In fact, this probably wasn't even 3 and 2. This might have been 2 and 2 for each one. Okay. The next question will be from chapter 21. And really, I got some choices for chapter 21. It'll either be something dealing with potentials, potential energy or electric potential, or it'll be capacitors, which could also include these here, or some combination of both. But it's going to heavily lean on one of those. This time, just looking at it, you can tell I heavily leaned on the capacitors. And what I said is, here's a circuit diagram. Here's some values for C. There's a weird space on one of those. Sorry, just the fact that it's 5.0 and then a space here. That space is a typo. What is the equivalent capacitance? If I want to find the equivalent capacitance of the circuit, what I'm going to do is I'm going to start looking at simplifying it. What I can say is that C1 and C2 are right in line, and they as a unit are in parallel with C3. And so I'll take this and say, I'm going to start by putting C1 and C2 together. And I'm going to say if I want to put C1 and C2 together, I can claim I have a C12. Now they were in series. In series, when you add capacitors, it's 1 over the equivalent capacitance is 1 over one capacitor plus 1 over the other capacitor plus however many you have. And so that C12 I wrote there, I can find like so. It'll just be 1 over 15 microfarads plus 1 over 5 microfarads. 1 over 15. 1 over 5 is the same as 3 over 15, which is 4 over 15. Couldn't just make it to be a nice number, could I? But that's not C12, that's 1 over C12. So therefore C12 is 15 microfarads over 4, or 3.75. And that's saying if I take this guy, that's what happens when I put together C1 and C2. Why can't I make that more narrow? But that's just those two put together. What I'm left with two capacitors in parallel. That C12 and C3 are in parallel to each other. And so I can take those two and put them together also. And say if these two are in parallel, I can have a C equivalent where I just add up these two capacitors in parallel. Now in parallel, capacitors just add. So C equivalent is just going to be C12 plus C3, or 3.75 microfarads plus 6 microfarads, or 9.75 microfarads. And there's my answer. Okay, part B. How much charge is on each capacitor? Well, here's what I know. I should have given myself more space so I could work my way up better. I know if I look at just this bottom picture, if I look at just this guy, and I'll move it over here for a second. If I look at this guy, what I can say is that this C equivalent, and here, has a voltage of V equivalent, which is a voltage of the battery at 12 volts. Because if that's the only thing in the circuit, that's the voltage it gets. You can just argue that with a Kirchhoff loop. But that C equivalent is made up of two capacitors in parallel. And anytime you're in parallel, the voltage of each piece is equal to the voltage of all the things that make it up. Because it's in parallel, that means that might be the voltage on V equivalent, but that's also the voltage on 1, 2. And that's also the voltage on 3. Because they're all in parallel. And so I know the voltage on both of these guys instead. Now, that's only the voltage. I asked for the charge. But for a capacitor, Q equals CV. So Q12 equals C12 V12. Or C12, 3.75 times 10 to the negative 6 farads, times V12, 12 volts. Which is, you know what, I didn't even turn in the 10 to the negative 6. I just put it as 3.75 microfarads and just said it was 45 microcoulombs. But you go say 45 times 10 to the negative 6 coulombs. Q3 equals C3V3, or 6 microfarads times 12 volts, which is 72 microcoulombs. So there's one part of the answer. I know this guy. But as for C12, C12 is made up of two capacitors in series. And all capacitors in series have the same charge. So C12 is 45 microfarads, but what that means is Q1 equals Q2 equals that, because they're in parallel, or because they're in series. And that gives me all three. Q1 is 45 microcoulombs, Q2 is 45 microcoulombs, and Q3 is 72 microcoulombs. I work my way down to find the I work my way down through these to find the equivalent capacitance, and once I do, I work my way back up to go and solve for everything else. Now there was a part C, how much energy is stored in capacitor 1. There's a lot of equations for energy in capacitor. Oh, that's not a, there is 1/2 CV squared. There's also 1/2 QV. There's also Q squared over 2C. Really, this is the main equation, but if I plug in my Q equals CV, I can solve for all the others. And I can just use one of these. Now, I chose to use, that's a G, Q squared over 2C, because I don't know the voltage on that capacitor. I could solve for the voltage on that capacitor, but I don't know it at the time. And I remember this when I was grading this. I have some students who did decide to use one of these other equations, and they solved for voltage, and they got full credit for it. I'm pretty sure I gave like my grading rubric was to give points for this equation, but if you use one of the other three, you could also get the points. And that's 45 microcoulombs squared over 2 times 15 microfarads. And doing that math, you get 6.75 times 10 to the negative fifth joules. Once again, this problem was graded heavily on partial credit. I want to say it was 2 points, 2 points, 2 points, 2 points for each answer. So 2, 4, 6, 8, 10. That's actually a lot for the answers because there was 1, 2, 3, 4, 5. Yep, there was 5 different answers. But the rest of the points were for knowing how to do this, knowing to do this, knowing these equations, knowing everything in here, with heavily with partial credit. Questions? I still won't guarantee it will be capacitors and parallel in series. I might do something with potential instead. Oops, that's not what I wanted that to be. To know what I decide to do, you'll find out Friday. What's this do? Ooh, I can shade things. The third problem is gonna suck. I'm sorry. I try. I'm trying, and I'm gonna make a point to make the numbers as nice as I can. The third problem will be a Kirchhoff loop. It's one of the more annoying things we did, and I acknowledge that, but it's one of the more important things we did. It's going to be a Kirchhoff loop. And I'm going to ask you for the current in multiple spots. I'm not going to guarantee how many, 2, 3, or 4. I probably won't do 4. 4 takes way too long on an exam. I won't do 4. But I'm going to ask you to find the current on multiple spots for a complicated system. And I will ask for not only the magnitude of the current, but the directions of the current. And this was last semester's. Find the current pass through resistors 1, 2, and 3. And say if they're going up through the resistor or down through the resistor. And I gave all the values. I will try to make the numbers nice. I'll try my best. They won't be perfectly even numbers necessarily. I am randomizing numbers on the exam, but I've made some effort to make sure that by random, I mean like I was setting the values. So I tried to make it so that all the values still come out somewhat reasonable so it doesn't get too ugly. But if I'm going to solve this, which I'm about to do, I want to solve for these 3 currents. The first thing I have to do is arbitrarily pick the direction of each current. And because each current's either going to be going up through the resistor 1, 2, or 3, or down through resistor 1, 2, and 3. And I'm just going to pick directions. It doesn't matter what I pick, or if I'm right, or if I'm wrong. I'm just going to pick directions. The idea is these directions are just a starting point. And this is what I chose. Up the sides, down the middle. Once I do that, I'll make my equations. See what my equations say. I have 2 rules. The first is the junction rule. And the junction rule says for any junction, current in equals current out. If I look at the area around those arrows, I can see that I1 and I3 goes in. I2 goes out. So there's my first rule. Then I have to make my loop rules. Now for my loop rules, I have options. I could go up and do just the left side. I could go and do just the right side. I could also go and do the outside. I have to pick 2 of those. And it doesn't necessarily matter which 2 I pick, as long as I use 2 of them. You could do any 2 of those 3 and it will work. I graded this heavily on making 3 equations, this counting as one of them. But yeah, I'm going to pick 2 to use. You don't necessarily need to pick the same 2 I did. I'll make it so you can use any of them. But let's go through and let's go with it. What I'm going to do is I'm going to start with the left junction. Coming here, up here, here, down, there. Now, if I do this, I know over any closed loop, the total potential drop is 0. And if I make my way up, which, you know what, I'm going to switch the color to something that isn't being used here, which is most everything, blue, just because the resistor. So I'm going to make my way up. So the first thing I do is I pass a resistor. Now, if you look at the way I measured the current, if you follow that around, I said the current was up and I went up. Anytime you move over a resistor in the same direction of the current, you have a voltage drop. I then go over the battery, and I'm going from the small side of the battery to the big side. That means I'm going negative to positive. When you go negative to positive, that means you add the potential. I then come around and get to the next battery. Now this battery, I'm going to the big to the small. I'm going positive to negative on this battery. I'm in this battery backwards. If you go positive to negative on a battery, you subtract the potential. And then I pass over the second resistor. Now that resistor, I too was down, I went down. I went in the same direction. So that's also negative. Resistors care what direction you're going relative to the current. Batteries don't give a shit what direction the current is. They care about what direction you're going relative to the battery itself. So there's my first loop. For my second loop, I'm going to do the right-hand side. And I'm going to start here, go up, and then down the middle. And we use green. And so I'm just going to give myself some space and do it down here. And so I'm going to start here, and I'm going to make my way up. I go over resistor 3 in the same direction of the current. I then go over V3 in the same direction as the battery. I then go over V2 in the wrong direction. Over R2 with the current. And then through R4 with the current still. And that's I3 R4. Got to be careful though. If I wanted to do the big loop, I could, as I said, but I didn't use that. And I'm not going to bother writing out the equation unless one of you want me to show you the equation for the big loop. If anyone does, let me know and I will.
That's all right. I think I got it with the 2.
All right. So there you go. I got my 3 equations. What I'm going to do is I have 3 equations and 3 unknowns. I'm going to have to solve them together. How I like to do it is there should always be one term in all 3 equations. In today's example, it's I2. Because I have I2, I2, I2. And so I'm going to take my loop equations and I'm going to rearrange them and solve for the other thing. I'm going to solve this one for I1. So I'll add I1, R1 to both sides. And say that I1 equals V1 minus V2 minus I2 R2 over R1. Now, you know me, I hate to plug in numbers ahead. I would never plug in numbers. Kirchhoff loops are like the one exception. I could work with like this, but Kirchhoff loops, if you plug in numbers ahead, I won't blame you because they can get ugly. And if I plug these numbers in, it made me look a little nicer. So let's see, V1 is 13 volts. V2 is 3 volts. R2 is 10 ohms. And R1 is 5 ohms. I'm gonna, damn. I was hoping to leave myself enough space, but I didn't. So good thing I color coded. We'll come back to that line in a second. So 13 minus 3 is 10 volts minus 10 ohms I2 over 5 ohms, which is going to be 2 amps minus 2I2. Meanwhile, my green equation. I2 is the thing in everything. So I'm going to solve for the part that isn't I2. So I'm going to add I3 all 3 and I3 all 4 to both sides. I'll factor out an I3 from this side. And divide. V3 is 8 volts. V2 is 3 volts. O2 is 10 ohms.
Could you move down the paper a little bit?
Oh, yep. Sorry. And that's over 4 ohms plus. Nope, that's a lie. 3 ohms plus 2 ohms, which is 5 volts minus 10 ohms I2 over 5 ohms. I'm just going to kind of shove this in the bottom. So that is 1 amp minus 2I2. What I'm now going to do is I'm going to go back to this equation up here, and I'm going to plug shit in. What I mean is I1 was 2 amps minus 2 I2. I3 was 1 amp minus 2 I2. I'm just plugging this in for I1 and this in for I3. Simplifying this, that is 3 amps minus 4 I2 equals I2. So I'll add that I2 stuff to both sides. 3 amps equals 5 I2. And therefore I2 equals 3 amps over 5. I thought I made it a nice number, but I guess I didn't. Or 0.6 amps. I guess it's a nice-ish number. I make the problems up myself. It's not always easy to get a nice number. I'll then go and solve the other bits. For I1, that'll be 2 amps. Oops. 2 amps minus 2 times 0.6 amps, which is 2 amps minus 1.2 or 0.8 amps. I know I'm being bad with sig figs. That should be 0.800. I'm being lazy. And for this green one, 1 amp minus 2 times 0.6 amps. So it's 1 minus 1.2 or negative 0.2 amps. And I got all 3 values. I1 is 0.8 amps, I2 is 0.6 amps, and I3 is negative 0.2 amps. But let's talk about this negative real fast. Really? Negative current just doesn't really exist. If you get a negative current, what that means is when you arbitrarily guess the directions, you guess the directions wrong. So I1 is 0.8 amps, and I1 is up. It's up because that's the direction it said it is. I2 is 0.6 amps, and it's down. It's down because that's the direction I said it is, and I got negative. I3 is 0.2 amps, and it's 0.2 amps down. It's down because I got a negative, which means this was off, and I have to flip the direction of the current. That being said, if I sold for something this guy first, if I got the negative thing right away, when you're plugging into the other equations, like let's say I2 ended up being negative 0.6, Make sure you plug it in as a negative in the other equations when you plug in. Now, grading rubric. If I remember correctly, I want to say 6 points per equation. Once again, this is by memory, but it was 6 points, 6 points, 6 points. No, it can't be that. 2, 4, 6. Either way, what I do remember is that each value in each direction was 1 point. So 0.6 was a point, up was a point. 0.8 was a point, up was a point. So only 6 out of 25 was for the final answer. I will give most of the points for getting your three equations. This is the big thing. If you find yourself running out of time, just get to those equations and go to another problem. I'm going to minimize the amount of points for solving the end of this because it's just ugly math. I care more that you can make the loop than you can do the math. I'm really sorry I had to bring home my grading rubric. It never dawned on me. I can probably figure it out again. 1, 2, 3, 4, 5, 6, 25. That leaves me 19. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I can't remember it. 12. Yeah, I don't remember it. Sorry. Any questions?
Nope, I'm pretty good.
Okay. The last.
I was actually.
Oh, sorry.
Oh, I was just
Go for it.
saying. I was actually hoping you'd go over a question like this because this is on the previous homework. I had trouble with this one, so.
Yeah, they're annoying. I'm not gonna pretend they're not.
Yeah, like I did fine with the one before, but then once they added the 3 batteries, and I don't know, it just confused me.
Well, hopefully that helped. There we go. Okay. I can't scroll up high enough on this one, so I had to do it like that. The last problem will be about magnets because it will be on the last chapter. I could do a lot of things. I could do a magnetic field from a current carrying wire. I could do magnetic field from a loop of a wire. I could do magnetic field from a solenoid. Meanwhile, I could do force on a charged particle. I could do force on a wire, or I could do torque on a loop. It's going to be something involving all that. And no matter what, you're going to have to use some right-hand rules. I selectively pulled 2 of the right-hand rule pictures to match what I'm doing. That's not all of them, keep in mind. There is also force on a wire and magnetic field of a solenoid. Kind of funny I didn't redo this picture. But let's go through what I had. And I said 2 current carrying wires run as shown in figure A below. I1 is 4 amps. I3 is 2 amps. D1 is 20 centimeters. D2 is 30 centimeters. What is the magnetic field at point P? Okay. Before I work out what the magnetic field is, let's do the direction. And what I'm going to say is that for each wire will cause a magnetic field. And I'll use the right-hand rule, the one at the top of the screen. If I point my thumb in the direction of the current, my fingers will curl around to give me the direction of the magnetic field. So right hand, which I don't know if this looks like my left to you. Once again, I think things are mirrored. Should look like my right. And I'll say the first one, I is up. So I'll curl my fingers around. Now what I'll have here is that it's out of the page on this side and into the page on the other, which means it's also into the page over here. For I2 is down, and I'll use the same right-hand rule. And I'll say it'll curl around. And I'll say on the left, it's into the page, which means also into the page here. But on the far end, It's out of the page. And so if I want to find the magnetic field at point P, they're in opposite directions. One is into the page, one is out. Well, 2's were my lower, 1's were my upper. And so I say, okay, magnetic field from a long wire is mu naught I over 2 pi r. So in this case, the total magnetic field is simply B2 minus B1. Traditionally, I make out of the page positive. It doesn't matter. You can go the opposite direction because in the end, I asked for magnitude and direction. So you just base it off what value you got in what direction. And I was like, okay, that means it's going to be mu naught I2 over 2 pi. But let's think about this all here. R is the distance from the wire to P, so that's just D2 minus B1, mu naught I1 over 2 pi. And this is the distance from the wire to the point P, so that's D1 plus D2. A lot of people last year just put D1 there and got it wrong because of it. Because I didn't mean to be a trick, but apparently was, and I felt a little bad. I like to factor things out when I can. And I have 4 pi times 10 to negative 7 Tesla meter per amp over 2 pi. I2 is 3 amps over 0.3 meters plus 4 amps. And what are these guys? What's D1 and D2 respectively? They're 3 and not 3 and 4, that's the currents. They're 20 and 30 centimeters, so 50 centimeters, so 0.5 meters. My pi's cancel. 4 over 2 is just 2. So it's 2 times 10 to negative 7 times this mess, which this is 10. 4 over 0.5 is 8. So it'll be 2 times 10 to negative 7 Tesla meter over amp times 10 amps per meter minus 8 amps per meter. So it's 4 times 10 to negative 7 Tesla. Didn't even need a calculator. Now I got a positive answer, and I said B2 was my positive one. So it has to be in the same direction as B2, which is out of the page. Now part B says we put an electron at point P. And the electron, which has this charge, moves at a velocity of 3 times 10 to the 5th to the left. What's the force? Well, the force acting on this thing is going to be QVB sine theta. And so the force, well, it's an electron. My lights just flickered. That's alarming. Why are my lights flickering? Am I still on? I'm still on. Okay. If I disappear, I'm sorry. My Q is, I didn't actually put the negative sign. I just said an electron with charge. That is a mistake. Oh, I actually remember I did this mistake. And I, on the board, like, wrote, like, oops, negative. And I added the negative sign. I didn't fix it in the exam, but I noticed during the exam and wrote it on the board in big letters. So negative 1.6 times 10 to the negative 19 coulombs times its velocity, 3 times 10 to the 5th, meters per second, times B, 4 times 10 to negative 7 Tesla times sine of the angle. But the angle is 90 degrees because B is straight in and Q is straight to the left. And so they're 90 degrees from each other. And I can do that math. And I'm going to kind of drop my negative sign because my negative sign is just going to be direction. And say 1.92 times 10 negative 17 newtons. I could say negative, but once again, I want the magnitude of the force. I said magnitude and direction. Well, I just said include your direction. I think I would have accepted with the negative or without. But the important thing is the direction. So let's think about the direction. To get the direction, I need to do right-hand rule. So what I'm going to do is I'm going to point my hand in the direction of V, and I'm going to curl my fingers in the direction of B. Now, B was out of the page. So out of the page means I have to curl like this. And when I do that, my thumb points up, which means the force is up. But negative charge, that's where that negative sign came in. And since it's negative, I need to swap it. Anytime your charge is negative, you swap the direction. And so it is down. I had some teachers who told me for electrons use my left hand and for protons use my right hand. And I guess it works for some people, but I always found that more confusing. I just always use my right hand and know if there's a negative sign, shit's fucked, flip it. Technical terms, shit's fucked. Good thing I'm posting these on YouTube. Someday I'll get in trouble. Any questions? I mean, that's the general idea. That's what this exam is going to look like. It won't be identical, but it'll be the same idea. One chapter or one problem for each chapter. And basically you just take a picture of this right here, upload it. Giving you an extra 15 minutes to deal with the internet that I normally would. Sound good?
Yeah, sounds good.
Okay. I want to say one more thing before we stop. So today I reviewed for the exam that's Friday, which means I have Wednesday in the middle. So the question is what the hell we're doing Wednesday, which the answer is, my plan Wednesday is I'm going to log on and I'm going to do it as a more open review. I'll have a bunch of stuff on me. I'll be as prepared as I can for being in a state of, and if whoever signs on, I'll help with whatever you guys want as an exam review. And so basically come with questions. As long as there's some questions, I'll record it and post it. But if no one shows up and no one really has anything we need to work on, or if if we're just doing homework, like if someone asks me a homework question, I probably won't bother recording it and posting it. But any review we do will get sent for everyone online. But come if you want. Let me know what you want to see, and I'll cover that then. If you know you will definitely want me to do something Wednesday, maybe let me know ahead so I can prepare ahead. You don't have to wait for me as I go and find a problem. I also don't have the textbook here or a textbook here for me to steal problems from. It's in Delhi, so I'm going to have to find problems online. Other than that, I'll stop there. I'll go post this online, which if you're not in the room, you probably don't need it online. If you're seeing it online, you already found I posted it, so that's a really dumb thing to say. But yeah, we'll stop. Have a good day.